Now the class, this is part transistor, part 5. Now this is transistor as a switch. Yesterday we saw the circuit for the previous class, transistor session 4 was about the transistor characteristics in the common emitter NPN transistor common emitter mode. There we saw how the output characteristics varies, and we also saw there are 3 regions. One is the saturation region, then the active region and the cutoff region. All those were explained in terms of the output characteristic graphs. We also had a graphical study where we had V input versus V output. When V input was less than 0.6, you find, or up to V equal to 0.6 volt, which is required for triggering the transistor action, you find that IB equal to VB, it's not sufficient enough to forward bias the input side base emitter junction, and therefore IB is 0, IC is 0, and so if you include the LDD in the path of IC in the output section of the transistor, the LED will not glow, namely transistor will be off. But because ICRC is minimum, VCC minus ICRC will be VO, and VO will be equal to VCC, or VO will be maximum. So a low input means the transistor is off, means IB is 0, means IC is 0, means LED will not glow, means output is high. Now when this becomes greater than, supposing the VBE maximum to drive it into IC saturation is say 1 volt, So beyond 0.6 to 1 volt that it is, you will find 1 volt or 1.5 or whatever it is, 1 volt, it will become high enough to saturate on that side, and therefore IC will become a maximum. For that maximum, the potential drop across IC will be so high that the reverse bias at that junction will not be adequate enough to reverse bias the junction, and as a result you will have output so the high input means VI is greater than some optimum value that is required, point number 1, means IB is IB max, means IC is IC max, means LED kept in the path of IC will glow brightly, and means the output will be minimum. These are the findings that we should know. So to start with, it will be like this, and very soon at the level of 1.6 it will become very steep and decrease rapidly with increase of Vi, and beyond that, beyond the certain region of say 1 volt or whatever it is, it will become VO is nearly equal to 0. This is your cutoff region and this is your saturation region. The designer so makes his transistor in such a way that this difference between 0.6 and 1 is very small compared to the other regions, and therefore it is either in the off state or in the saturation state, and does not stay in the active mode for long time. This is your active region. It won't stay for a long time in the active region. This is what you should know, and based on this we are going to design our transistor as a switch. Now here, as usual, the circuit will be with base, emitter and collector, and here you don't need to measure the input and the output, you just want it to be less than cutoff or greater than VBE required for IC saturation. So you don't require any meter to measure. Instead you have your RB, and then it passes through to the positive of, because this is P, this is N and this is N, and this is base and this is collector and this is emitter. So this has to take its lead from the positive to the battery negative. Maybe you can regulate it to the optimum value so that it is either below the knee voltage or above the voltage required for saturation. So this is what is called as the V input. This is not signal. No signal is introduced because it's not an amplifier. This whole thing is going to serve as input or this thing. Now from the collector you have your RC, and in the path of this you have an LDD, which will either burn or will be blown out. Now RC, this is the RC, and here you have to, because this is N, you have to take its lead from positive, negative, and here, and emitter is earth. This is also variable. You can tune it to such a value that this becomes, even for low value of VC, that it is, you will find that it will be driven into saturation. More than that also, it will be in the saturated state. That's what we saw. Now here you have your VCE, which is equal to VO. This is the circuit. So now I'll have a tabular column to show the variation. Now what about your VN? Okay, what is IB? What is the implication for IB? What is the implication of IC? What is the implication for the status of or mode of state of transistor? What can you say about the PD across RC, and what can you say about the voltage at the output? Now VN, first one is VN is less than 0.6 volts. IB is 0, IC is 0, state of transistor is in the off state, PD across the RC is 0, VO will be maximum, because VCC minus ICRC equal to VO, VCE equal to VO, VCE equal to VO. So when IC is equal to 0, ICRC equal to 0, the entire VO will become maximum VCC. Now second, for greater than say 1 volt or 1.5, 1 volt, IB will be IB max, IC will be IC max, and the state of transistor will be on, PD across RC will be maximum, and output will be nearly 0. Therefore, a low input implies no base current, no collector current, transistor is in the off state, PD across RC is 0, and output is maximum. High input, which is greater than this, whatever is required for saturation, implies IB is maximum, IC is maximum, transistor is in the on state, and current through this is in this. And then what about the LED? LED, in the first case, when it is less than 0.6, this will be, here it will not glow, does not glow. And when it is greater than the mass, whatever is required for saturation, the on state maximum 0, and the LED will glow. This is the comprehensive tabular column. If you know this and if you cast this, definitely the examiner will realize you have understood the concept well, and you are sure of getting more than 90% of the marks allotted for that particular question. Now you have to show the arrowhead direction. IB is like this, IC is coming from here, and IE is going out like this towards the negative. This is your IE, this is my IC, and this is IB. So as usual, IB plus IC, both of which enter the transistor, equal to IE, which exits the transistor, as shown in the NPL. Next will be transistor as an amplifier. For the amplification action of this transistor, we are going to use only the active mode. Only in the active mode you have appreciable tellable gain, and so you are going to use it only as an amplifier, where a low input signal coming from a signal source, which is alternating and sinusoidally varying with respect to time, is manifest as a large amplitude output, also in the variation with a simple harmonic variation. The amplitude here will be magnified, will be multiplied by a certain factor called the voltage amplification factor, and that will be the amplitude at that end. Here you don't have to measure, you don't require an LED here, but RB, RC, VBB, VCE, VCC, VCE, and all these will remain. So what is the extra thing that you have in the concept of transistor as an amplifier is your signal, which has to be superimposed with the already existing direct battery voltage of VBB at the input side. because there are two problems in directly feeding the input signal itself without the use of accessory battery of VBB. Point number one, the signal will be very small, so even the amplitude value will put it in the cutoff region, if at all it is going to forward bias. And for one half, if it is going to forward bias, for the negative half of the AC, that it is going to vary with the V signal I am talking about, which is going to vary from positive to negative halves as a sinusoidal function, sine curve with respect to time. When it is in the negative half of the cycle, it will it will reverse bias the input side. Base emitter will be reverse biased whenever this is in the negative half. When it is in the positive half, it may forward bias. In the negative half, it may reverse bias. So you have to couple this small variation that you have along with superimpose this over this VBB, so that the input either becomes VBB plus the amplitude of the signal, or amplitude means varying voltages of the signal, or it will be VBB minus, because supposing you have two batteries like this, this is positive half. Now if you have, this is going to base of the transistor, and this is going to the other side. Now here if you have positive is connected to negative, so this is VBB, this is V signal. So at any instant it will be VBB plus V signal equal to plus VBB during the positive half. During the negative half, this negative and positive of the VBB remains the same. I am not going to change the terminals there, but this will become positive and this will be negative. There is what is called a sum and difference method of computing the voltage. When the two positives are connected together and the negatives are going out to the external circuit, if you apply Kirchhoff's law for the negative half of Vs, now V input will become VBB minus Vs. Either VBB minus Vs or Vs minus VBB, and it will take the sign of the greater one. If VBB is not sufficiently high compared to Vs, this factor may go to a negative. Again, I reverse bias the input junction for base emitter junction. So VBB should be very much greater than your amplitude of the Vs signal, Vs max, so that regardless of whether Vs is in the positive half or negative half, regardless of whether you are considering VBB plus Vs or VBB minus Vs, the direction of the voltage will be good enough to forward bias the base emitter junction. Very, very important, this VBB should be very much greater than Vs to ever forward bias. So bearing all this in mind, I am going to now superimpose. Also, the signal may be an alternatively varying, say AC signal that you say, that's what we are going to amplify. Transistor can only amplify the AC inputs, effectively alternately varying inputs, even if they are small. But VBB by itself cannot show any graph of variation of voltage with that. It won't be a sinusoidal curve. I want an amplified sinusoidal version of the whole thing, input as well as the output, for me to realize how it works as an amplifier. So this is the thing. So what you have to do is you have to choose your VBB sufficiently point number high, and you have to couple that. But the input signal may contain both DC components, some DC components may also be there, from fractional DC parts will also be there. You have to rule out the DC from the AC. The DC from the VBB is okay, but the DC components from here should not intervene. So to rule that out, you have your circuit like that. This is the base, this is the emitter, this is the emitter, this is the collector, and this is the base. This is P, this is N, and this is N as well. Now you have to pass it through RB, and as usual take to the positive, negative, and take it like this. And here you have your input signal through the body of a capacitor C1, so that you have your small input V. This is your V input signal. VIS is input signal. It varies sinusoidally with respect to time, but the amplitude is very small. Now here this will be coupled along with this, and therefore it is either in parallel or sum and difference. and only the DC components that are AC components that are coming out of here will add to the already existing constant voltage here, and that will be given as this thing. And here again you have your RC passing through P, etc., and then going here, emitter is earthed, and here you will have another capacitor C2, and here you will realize your output. Now it can be shown that the output here will go like this, not there will be two informations, the amplitude would have become bigger compared to the amplitude here, point number 1. The trend will be, it will first take the negative half and then go to the positive half. For an input going in the positive half and then going to the negative half. If you have like this input, the output will go to the negative half and then go to the positive half. These are the things that you should know. This is also tunable, not with the idea of varying these, but setting them for suitable voltages to put it in the active region. When superimposed with Vs, whose amplitude value is by far very small compared to your VBB here. And here there are two capacitors which will filter out the DC components and block the DC components and send only the AC parts to the outside. As usual, the emitter will come out here, IE this will be, and this will be my IB, and this will be my IC, and so the equation IB plus IC equal to IE holds good. Now this is the thing. Now when during the positive half of the input signal, already it will become VBB plus something. So over and above the 2 volts, supposing this is 2 volts, over and above the 2 volts it will become 2.0001, 2.0002 and so on, because this is very small compared to 2. So it will go on increasing, maybe the amplitude is not 2. So 2.0002 will be the maximum. After that it will come down, VBE will be decreased and then reach a 2, not less than 2, reach 2, because 2 is constantly there, and then it will take a values less than 2, say 1.9998, 1.9996, again 1.9998, again 2 and so on. This is what is the alternate variations that come in the input side. Accordingly you will have an amplified output there, and this is what you will measure here. Now coming to the, I think I can, now that you have taken the circuit, for the mathematical part of the whole thing, I require the space for that, so you can refer to your own circuit diagram. Now coming to your now we know VBB equal to VBE plus IB times RB. Now for small changes in VBB, who is bringing the small change in VBB? The input signal. The AC component from the input signal, after the DC components from there are filtered out. That will either add or subtract with this. So if you differentiate or find small changes, delta VBB equal to delta VBE plus delta IB into RB. This RB will not change, it's a constant. Delta IB is a small change in the correspondingly the change in the IB. Now we know delta VBE by delta IB equal to, for a constant VCE, we are not going to change the VCE there, that is equal to RI, input impedance inherent in the transistor, not that which is externally connected here, into RI. More or less, because we are taking the sloping region, you can take it to be a constant, RI. Now this is your RI, therefore delta VBB can be written as VBB plus V input signal. Therefore delta VBB can be written as VI input. So VI will be equal to delta VBE equal to RI. Delta VBE, there this implies delta VBE equal to RI times delta IB. So you can substitute for R, this is the equation 1 and this is equation 2. So substitute for delta VBE in equation 2, you have delta VBB is equal to VI equal to RI times delta IB plus RB times delta IB equal to delta IB times RI plus RB. If these both together, I call it as R, the total impedance at the input side, you have R into delta IB. This is your equation 3. This is my VI. You just note this down and box this. So VI equal to R times delta IB. Now coming to the output side, this is equation 3. Coming to output side, you have VCE equal to VO equal to VCC minus IC times RC. IC times RC is what we saw. As earlier also we have seen. Therefore, VCE equal to VO equal to VCC minus IC times RC. Therefore, if you differentiate this, delta VCE equal to delta VCC minus delta IC times RC. Now delta VCC is going to be 0. Is going to be 0 because VCC is going to be a constant. Therefore, but delta VCE is nothing but VO. Is nothing but VO equal to minus delta IC times RC. Or in other words, and also from the characteristic curves we saw current gain beta equal to IC by IB is also equal to delta IC by delta IB. This is equation 4, this is 5 and this is equation 6. From 6, delta IC equal to delta IC will be equal to beta times delta IB. Therefore, your VO will be equal to minus of beta times delta IB times RC. So, amplification, voltage amplification factor AV equal to VO by VI equal to minus beta VO minus beta delta IB times RC by VI is R times delta IB. Delta IB cancels, it is minus beta times the ratio of the resistances at the C output and the input side. This will be my voltage amplification. The negative sign shows that whenever this is increasing, that is decreasing and vice versa. How it varies and how you get the graph will be done in the next session. So to sum up, you find that the output is out of phase with respect to the input by a phase of 180 degrees because it is coming as a minus here. And point number 2, the output voltage is several times the input voltage of the signal. So it will have 4 times the amplitude there at the output side and hence you get a alternately varying, sinusoidally varying output, no doubt, but the sinusoidal varying output is amplified output. That next we'll see in the next session 6. Thank you.